We now take a look at another algorithm that's designed to help us solve linear systems, and that algorithm is called Gauss-Jordan elimination. And what it does, it takes Gaussian elimination a step further, or maybe several steps further. And what it does, it eliminates, no pun intended, the need for back substitution, right? So what do we mean by this? Well, it's best if you see an example. So what I'm going to do is write down an augmented system, but it's already in the form where I have created that triangle, right? So let's consider this system, right? And I'll make it a little bit bigger than the examples that we've recently done. This will be a 4x4 system, 4 equations, 4 unknowns, and here it is in augmented form. Right. So if you notice, we have all the zeros in the desired positions that would make a back substitution quite straightforward, right? And also, if you notice, I have all the pivots, all the leading terms are 1. And again, just in case you're wondering, yes, this is an augmented system. These are the coefficients, and then these are the b's, right? So if we were to use back substitution, in fact, let's go ahead and do back substitution and see what results. Now, when no particular set of variables are indicated, you can always use the standard ones like the x1, x2, x3, x4, and so forth. So the bottom row here tells me that x4 is equal to -6. The third row tells me that x3 plus 5 times x4, so that's 5 times -6, is equal to 0. So that means x3 is 30, right? So x3 is equal to 30. And then the second row tells me that x2 minus 2 times x3, which is 30, plus 3 times x4, which is -6, is equal to 6. And I'll pause for a sec. Well, you can actually pause the video for a second, do your arithmetic, and what do you end up with? Well, you should end up with x2 equals 84, right? Because all of this adds up to, this is a -60 minus 18, so that's a -78. Add 78 to both sides, you get your positive 84. And then finally, what do we have? So x1 minus 2 times x2, which is 84, plus x3, which is 30, plus 0 times x4, which I don't have to write, but I will just for emphasis. That's equal to 1. And then isolating x1, again, do your arithmetic, and you should end up with 139. So here's our unique solution: 139, 84, 30, -6. And this is my unique ordered quadruple. All right, that's great. But if you notice, like you said, we had to do some arithmetic here in our back substitution. Wouldn't it be nice, right, if in addition to eliminating all these entries below the pivot, right? So these 3 pivots were used to eliminate these. I mean, I didn't show the steps, but we've done the steps quite a few times now. But in addition to eliminating these entries, what if we could eliminate the ones above, right? So for instance, this and I've used this word diagonal before, right? So basically, these entries are on the diagonal. If we and now we have 3 elementary row operations that can be used to eliminate these 6 entries. Why can't we apply those same elementary operations to eliminate these 6 entries? And what that would do is, yes, it would adjust the constants on the right hand side, but it would eliminate the need for these extra steps of back substitution, right? We will still have to do some extra arithmetic, but the question is, do we do it again in our nice convenient augmented form, or do we choose to do it via back substitution, right? Now, given the choice, I would just continue my elimination, right? So let's see what it would look like if I now, in fact, what I will do, since I kind of, made this a mess, I'm going to restate the augmented matrix and then do my elementary row operations. We just have to think carefully now, how are we going to eliminate that other triangle of entries, right? If we can do that, then yeah, we would have been able to solve the linear system without the back substitution. All right. Now, there are different ways you can do it, and there is no one specific order in which it has to be done. But the key now, for instance, is to realize that I tend to do it this way. Like, I usually start in the upper left entry, get my pivot there. Hopefully that's a possibility. And then first eliminate all the entries below the pivot in the first column. Then have my pivot in the second column, eliminate all those entries. And then move to the third column, eliminate all the entries below that pivot. And then just kind of go back now, go upwards. Once I get to this point and I have my pivot here, right, I'm going to use this now to eliminate the 5 and the 3. Now, this entry is already 0, but if this was a non-zero entry, then I would use that same pivot. So this is now my pivot to eliminate the 5, the 3, and then that will create my zeros here, right? And then once I have that, now see, having these zeros in this bottom row, when I do my row operations, it's not going to affect any of these. The only thing that will change using this as my pivot, right, will be I'll be able to eliminate the 5 and the 3, and then the constants on this side will change. So let's see if we can figure out what the operations are. So I'm going to, in fact, yeah, let me just do it in one row instead of going across and down, across and down. Let's do this. I'm going to take, since I want to eliminate the positive 5, I'm going to take a -5 times row 4 and add that to row 3. And then I'm also going to take a -3 times row 4 and add that to row 2. That will eliminate the positive 3. So these two operations produce this augmented system. So what I'm going to do now, since I know that none of these will change, I'm going to write the first 3 columns like that. And then now let's do our arithmetic, right? So -5 times row 4, we'll make this a -5 plus 5. That will give me a 0 there. And in fact, let me go ahead and draw my line, put my -6 there. Now, -5 times -6 is 30, plus 0, that's 30, right? And now let's, using this operation, again, with my pivot of a +1, if I take -3 times row 4, added to the second row, that will eliminate the +3. And then what I have is -3 times -6, that's 18, plus 6, that is 24. So like that. All right, perfect. And then, yeah, this is a 0, because that was already 0, and then the 1 doesn't change. So that's my new augmented system, right? And now, if you take a glance at this, look at the fourth row, because it doesn't change, it still tells me that x4 is equal to -6. There it is. Now look at what the third row tells me after I've eliminated this entry that was +5. I now made it a 0. So all that's left in this third row, the information in this third row, is that 1 times x3 is equal to 30. So that means x3 is equal to 30. And look, that's what we have right here. Let's continue. So now, since I have zeros above this pivot, here's my other pivot, and now I'm going to try to eliminate the -2 and then the +1. So again, I'm just going to circle what is now my pivot, and I'm going to use that to eliminate every entry above that circled 1, right? Okay, so let's say, so to eliminate the -2, I'm going to have to take +2 times row 3 added to row 2. And then to eliminate the +1, I'll have to take -1 times row 3 plus row 1. And those two operations will give me yet another augmented system. So now 1, 0, 0. The first column is done. Now the fourth column is done. It's the second and third columns we have to work on. So -2, 1, 0, 0, 1, -2, 1, 0, and then 0, 0, 0, 1. Oh, wait, no, why did I do that? I didn't perform my operation, so actually let's do, yeah, so it's really, yeah, what will change is this one, and then the constants. All right, so we have 0, 1 there. So now take +2 times this and add it to the row above. That will eliminate this -2. It will make it 0. And then 2 times 30 is 60. Plus 24, that's 84. And look, that's what this is right here. So you can see the solution that we obtained earlier by back substitution. You can see that solution presenting itself in this kind of, this extension of Gaussian elimination. Right, and then finally, to eliminate the 1, what do we have? It's the negative of this plus this. So the -1 plus 1 is 0. Again, 0 plus 0 is 0, and then I have to take the negative of this, which is -30, plus 1. That's -29. Right. Okay, so we are so close. All we have left now is to eliminate this -2. And in order to do that, we use this as our pivot, right? So again, let's see. So one more operation. Yeah, let me write that down and then just say a few more things about this process. So to eliminate this -2, we're going to have to use a constant, or k would be a +2, multiply the second row and add it to the first row. So 2 times row 2 added to row 1. All right, so now we know what's not going to change, right? So I'm going to write the rows 4, 3, and 2, because those won't change. 1, 0, 30, and then 0, 1, 0, 0, 84. And now let's finalize what's going to happen. So if I double row 2 and add it to row 1, I will have a 1 there. This now becomes 0. These two zeros are unchanged. And then if you take, so 2 times 84, that is, what's that, 168. And then plus -29, that gives us 139. And that's what we got by using our back substitution, right? But now, with these 4, I guess you could say, well, 5 additional elementary row operations, we were able to create that desired additional triangle of zeros here. So we now have a triangle there, and this was already given in the setup. And when that happens now, if you were to take this and write the system in standard form, the bottom equation tells me that x4 is -6, because all the other coefficients are 0. The third row tells me that x3 is equal to 30, again, because all the other coefficients on the left-hand side of the system are 0. The second row tells me that x2 is equal to 84, and then finally x1 is equal to 139. And if we want to write that as an ordered quadruple, we get exactly what we got before. So now this process of having all your pivots be equal to 1 and then eliminating all the entries below and above your pivots is called Gaussian elimination, right? So the process, it's Gauss-Jordan elimination. So the process of eliminating all entries above and below the pivots is called Gauss-Jordan elimination, right? So it takes Gaussian elimination one step further. So essentially, without being told explicitly which elimination to use, if we have a linear system, right, no matter how big, there are two things that we can use. We can use Gaussian elimination plus back substitution to solve, right? And that's what we've done up to this point. And now this new process of, again, sticking with our elementary row operations, but just eliminating more terms, whether you think of them as terms in the equation or entries in the augmented system, using Gauss-Jordan elimination, it eliminates the need for the back substitution. I really do like that pun. So Gauss-Jordan elimination eliminates the need for back substitution. Now you might wonder which one is more efficient. Well, for a general system, it turns out the additional number of row operations that you have to do in Gauss-Jordan is roughly, if you use the number of arithmetic operations that you have to do, is roughly on the same order of the amount of algebra and arithmetic you have to do with back substitution, right? But I just think this one is helpful, and we will see later on using Gauss-Jordan tends to be preferred in certain situations, right? But there you go. So these are the two fundamental approaches. In my mind, it's kind of it's the same philosophy. Gauss-Jordan just takes what Gaussian elimination does, takes it a little further. So now you have two things to choose to use as tools while solving linear systems. So have fun.